Thank you, everyone. Good evening. Thank you so much for being here. And thank you, Wolf, for having me here and giving me this amazing opportunity to talk about some of the stuff that I work on and dearly love. Uh, so I'll be talking about unraveling the mystery of dark matter with stellar streams. So just by a raise of hands, how many of us have heard the word dark matter or know what it, okay, so that's quite nice. Good. So I won't go into the detail. I'll just kind of surface through dark matter and eventually come to the stellar streams, which might be a new subject for most of us. So at this opening slide, what we are seeing is the Milky Way galaxy. And of course, the Milky Way galaxy is sphere. So the entire three-dimensional sphere is projected here onto the 2D plane. So what we are seeing here at the center is the stellar bulge, the galactic bulge, and the disk of the Milky Way, and then the halo around it. These colorful stars, these colorful dots that we are seeing are basically stellar streams that I'll eventually go into. But I just also wanted to give you this perspective of the image because we'll be seeing lots and lots of figures like this today. Right. So before I really move to stellar streams and dark matter, let me just put everything in perspective so that the problem is clear, so that ultimately the solution, if we arrive at any, would also be clear. So our home galaxy is the Milky Way galaxy, and this is what it looks like. This is the most updated portrait of our backyard. So what we are seeing here is the sun, where we stay, and it's a complicated structure. It's a massive, colossal, complicated structure, the Milky Way galaxy, just like any other galaxy. So this is like a side view of the galaxy, and this is what the Milky Way would look like from above, from the top, if we could ever send a satellite that far that it could picturize the Milky Way. Of course, it comes from a simulation. So at the center, this really dense, packed, spheroidal structure that we are seeing is the stellar bulge. Over here, this is the disk with some spiral arm features that you can see over here, which are turning around like a fan on the ceiling. And some other structures as well that I'd probably surface through as we go along. Just trying to describe also the sort of parameters that astrophysicists usually deal with so that things are in better perspective. So we believe that the age of any galaxy in the universe, more or less, especially the Milky Way, it is 13 billion years old. But we usually refer to it as giga years. So 1 giga is 10 raised to the 9. The size of the Milky Way is 100,000 light years. So that's equivalent of saying that light would take 100,000 years to transfer from one end of the edge of the galaxy to the other edge of the galaxy, from here to here, for example. The rotation period of a typical star is 250 million years. So this disk, every point that we're seeing here is basically a star. And a given star in the disk typically takes about 250 million years to completely come back to the same position. Which basically means that right now sun is here, but about 65 million years ago, when we experienced the extinction of dinosaur, the sun would have been quadrant away somewhere at this position. So that's perhaps the place where sun would have been when the dinosaurs went extinct. The Milky Way is really massive, so it's 1 to 1.5 times 10 to the 12 solar masses. So it's equivalent of saying that the total mass of the Milky Way can be imagined to be if there were 10 raised to the power 12 number of sun like ours, for example. And of course, mass of a sun is 10 raised to the power 30 kilograms. So this is, in more or less in absolute terms, the mass of the Milky Way, or typically of any of the galaxies in the universe. So the numbers are gigantic, of course, as one can imagine. Zooming out a bit, from the Milky Way, which is here, which is our home galaxy, we have other structures in other galaxy in the local group as well that we call local neighborhood or local group. And the local group is dominated by two structures, which can be seen here, the Milky Way and our neighboring galaxy, the Andromeda Galaxy. Of course, there's third galaxy as well, but these two galaxies really contribute most of the mass in the local group. So the dynamics of the local group, how stars are moving and how galaxies are moving, is dominated by these two structures. Of course, there are other structures as well that are marked here, which is like the sibling galaxies, the satellite galaxies that we call. Like Earth has its own satellite moon. Even galaxies, which are the parent galaxies, have their own siblings, have their own children, which are called satellite galaxies. There are more structures that are shown here in this figure, but then it would have been really crowded if all those structures were pointed out in this figure. And of course, we know, zooming out a bit more, the universe is teeming with galaxies, right? So we have all sorts of galaxies interacting, merging, which are of different masses, density, scale, luminosity, surface brightness, matter content, temperature, chemical composition, dynamical history. So there's varied variety of it. And when one observes it, the natural question that is raised is, of course, how these galaxies came into being, why are they the way they are, and how did they form in the first place? So for that, we have a recipe, which is the LambdaCDM model. And I'll detail a bit on it what LambdaCDM is. But it is basically a recipe to create our own universe. So physicists have sort of figured out that what are the ingredients that we really need, more or less, qualitatively speaking, that could eventually produce universe in our simulations, in our computers, that would more or less look like the universe when we make an observation. So then we've come up with this argument that about 4.6% of the energy density of the universe is stored in the form of atoms that we imaginatively or intelligently call baryonic matter, but it's really the luminous matter. So anything that we are made of, Earth, planets, stars, gases, galaxies, galaxy cluster, anything that's made up of atoms or baryonic particles that we can see in the electromagnetic spectrum, contributes only 4.6% to the total energy density of the universe. The rest, approximately 24%, comes from what is called the dark matter. So dark matter is the non-luminous matter, and it's non-luminous because it does not interact with light. There are theories that say it does, but then it does so minimally that it would never be observed, perhaps, at least in the electromagnetic spectrum. So we cannot really see it. So it doesn't matter how big of a telescope we big with large eyes and large lenses. It could very well be the case that we'll never be able to visualize the dark matter particles. The rest, 71%, is stored in what is called dark energy, which is the cause of the expansion of the universe. So the universe is expanding, and it's dark energy that's behind it. But the real motive of the talk, the focus of the talk, would be dark matter and these atoms, because this matter, the luminous matter and the non-luminous matter, is what dominates the dynamics of the universe at galactic or subgalactic scales. So now, with our ingredients in hands, we are ready to cook our own universe. So what we'll do is that we have an equation for the dynamical evolution of the universe, because universe is a dynamic system. So more or less the function that we put, so we have the ingredients, and now we have a function which controls the evolution of the universe. And that function, of course, has parameters such as the fraction of atoms in the universe, the fraction of dark matter in the universe, the fraction of dark energy in the universe, because we want our toy universe also to expand, and various other cosmological parameters as a function of time, because the morphology or demographics of the universe is also changing with time. So we take our wonderful equation, and we take the ingredients, and we put it in a very supercomputer, because we want big computer which can basically handle tremendous amount of parameters and so on. And of course, we want to simulate, we want to run a simulation, we want to basically make a game that can run for 13.4 billion years. Of course, it happens on a period of weeks or months, but eventually we want our output to sort of look like what universe would look like after 14 billion years, because that's the age of the universe. So here is one of such simulations, which comes from the Aquarius project. So here what they have done is that they have taken all these ingredients, the gases, the atoms, the dark matter, and the dark energy, put it in an equation. And what we are seeing here is the evolution of the universe shortly after the Big Bang. So you see, so as the universe evolves in time, there are these potential wells, potential traps that are formed in different locations of the universe. And these potential wells basically trap and attract more matter, more dark matter, and more stars within it, forming more structures. So all the nodes that we are seeing here basically are individual galaxies. So it's really zoom out cosmological simulation, and all the purple particles that we are seeing are dark matter particles, and these cosmological filaments, these web-like structures that we are seeing, are basically funneling all the matter into these nodes, forming bigger and bigger galactic structures. So this is called the hierarchical cosmological formation of the universe, and this is how we explain the galaxies that we are observing today would have basically formed over billion of year time. So now we are, of course, zooming in as the movie is progressing, because now we are focusing on, can we form something that looks like close to the Milky Way, or at least close to the galaxies that we observe in the local universe. So we see that, yes, we get something like the Milky Way, surrounded by those satellite galaxies that I showed you before that also exist in the local universe. So by running these simulations, of course, the idea is to understand the dynamics of the universe and eventually see how best we can describe, our toy model can basically describe or match the observations, because ultimately the idea is to match the observation to see what the nature is telling us and compare it with our theoretical predictions. So on large scales, LambdaCDM model works perfectly well. So here we are zooming into these nodes to see what structures look like, and more or less they look like the galaxies that we observe. So LambdaCDM model works exceptionally well at large scales, as can be seen here. So this is the structure of the universe observed by STS's survey. So it was a survey to observe the universe, and qualitatively speaking, it matches pretty well with the simulations that physicists generally run under the cosmological paradigm. So this is good. So at large scale, it's great. But then we realize that there are certain problems with this model, probably at smaller scale. So when we make small scale observations, not as big as this, but not as small as room as filled. By being an astrophysicist, for me, small means at galactic or subgalactic scale. So a few light years, of course, even bigger than solar system for that matter. So that's great. So the large scale is fine, but then some problems have incurred at smaller scales. And we really want to know the nature of dark matter, because the proposition is that the problem persists at small scales because we yet do not know the nature of dark matter. So we know that we need this additional matter which we cannot really observe, and it's non-luminous, and it most likely exists in the universe. But we do not really know its nature. What is its mass? What is its velocity? What are its fundamental parameters? So we are mostly concerned at galactic and subgalactic scales, the small scales, with the dark matter and the atoms, really. So atom is something that makes everything that we can see. And not so much for the dark energy, because dark energy doesn't really dominate at this small scale area. It dominates at really cosmological scales. So we are concerned with dark matter and normal matter for now. So the idea is to probably use somehow normal matter to infer the properties of dark matter. It would have been great. So the problem is pretty straightforward if you come to think of it. Had we been able to detect dark matter, right? So we know the properties of electron, we know the properties of protons, we know the properties of these fundamental particles, because they are luminous, they are baryonic, so they interact with light, and we can see these particles in these large microscopes that we call particle accelerator machine or particle detectors, because we can detect these particles, but that's not the case for the dark matter. So then people have for long relied on astrophysical observation, that can we use somehow astrophysics, the observation of the stars, the observation of the galaxies, to know something about this mass that is most likely invisible. So the smoking gun evidence for the very existence of dark matter came from the velocity curve of the galaxies, because you might ask that if we cannot see it, in the first place, how the heck do we even know that it exists? So this is the galaxy, and the idea of the velocity curve of galaxy is that as you go further out from the galaxy, so we are basically, so you can literally imagine that you're observing this galaxy and you have a big telescope, and you're basically pointing at different radius from the center of the galaxy and observing the velocity of the stars at different epoch. right? So when you do it for a given galaxy in the universe, the sort of velocity profile that you get, so on the y-axis you have the velocity, how fast or slow the star is moving, and on the x-axis you have when you're moving further away from the center of the galaxy. So the observation typically looks something of this sort. So there's an increase in the velocity for the stars, and as you move out, as you move further away from the center of the galaxy, the velocity profile more or less stays constant, which is fine. So that's the observation. That is what nature is telling us. Now we can't see dark matter, right? So, but what we can see are stars and gases. So the next normal thing to do is, of course, to take this mass distribution of stars and gases that we can observe, and then try and calculate using the high school physics formula of this form, and try and calculate what sort of velocity should we expect from the components, from the matter component that we can see. And when we do that, the expected curves look something of this sort. So this is the very familiar Keplerian curve that we also observe for the planets around the sun. So this is the Keplerian fall. So had there been only baryonic matter, only the matter and atom that we can see, then this is something that we would have expected. But that is totally not the case, as we can see that this discrepancy between observation and what theory was telling us. So at a given radius, so radius is something. So in this equation, radius is something that we can precisely observe, right? Because we know the center needs to be somewhere here, and we know where we are pointing. So basically, the radius part is fine, and v, the velocity, is something we can observe. So what we are trying to calculate is the mass in this equation. And then we need, basically what this equation and observation is telling us, that we need this extra mass in the numerator over here to also increase the velocity. So that question mark over there is what turned out to be the missing mass problem, the mass we cannot see, and ultimately physicists coined the term dark matter for it. And this constant velocity profile that we can see over here that is wonderfully defying the Keplerian fall is a ubiquitous phenomenon. So that's something we observe for almost all the galaxies in the universe for which we have precise measurements of the velocity. So it's not that Milky Way is an outlier or there's just a single galaxy that is probably peculiar. It is all the galaxies that is peculiar. Or the other way to put it is that we are somehow missing the fundamental law in the physics, or we are missing some fundamental property that is not allowing us to reconstruct this sort of velocity profile. So that was one astrophysics. So this velocity curve was the first smoking gun evidence that sort of indicated that there's this missing matter, and probably we need to account for it somehow in our cosmological simulations or in astrophysical analysis. Now, with time, there are a plethora of other astrophysical observations as well that now exist that also points towards the idea that, yes, there is some missing matter that needs to be taken into account. Whether you make cosmological observations like the famous cosmic microwave background map, or you observe galactic clusters and you sort of try to do gravitational lensing and try to infer the mass of very far-off galaxy clusters, and even that suggests that, so every point over here is a galaxy, it's not a star. It's a galaxy, most of the points that we are seeing here. And these galaxies are also moving in a blob of dark matter. And their velocities can only be justified because they're moving with great speeds. Such a great speed can only be justified by saying that there's this additional mass which is not visible in our telescopes. And same was for this orbit simulation, that the high velocity of stars in a given galaxy can also be justified, the sort of orbits that these stars have, by accounting for this missing mass. So hopefully now the problem is kind of should be clear, that LambdaCDM says that there's a major fraction of matter in the universe that is invisible, because most likely it is not in the property of the dark matter itself to be visible to us in the electromagnetic spectrum, which is dark matter. And more than 80 to 90% of mass in a given galaxy is sourced by the presence of dark matter, which means 0.9 fraction of matter in a given galaxy is dark matter, which means it's the main driver of the dynamics of the galaxies, or the galaxies for the nearby galaxies or galaxies at local scales. So we really need to understand what dark matter is. Otherwise, we'll always get these biases in understanding how the universe really evolved. The sort of indication is that, that dark matter is probably cold. By cold, we mean dynamically cold, so it's probably a massive particle that moves rather slowly. Not as slow as me, slow compared to the photons, basically, but it's non-relativistic. And it's also collisionless, probably, so if you'll have two dark matter particles, or if you just take any matter with dark matter, it will basically pass through. It won't collide. So that's one of the inferences that people have from observations, but it's still speculative. And also, we want to constrain the fundamental properties of the dark matter, because that's the ultimate treasure mine that we are after. And of course, our home galaxy, the Milky Way, is the best laboratory to study dark matter, because if it is coming down to astrophysical observations, because we haven't observed, really, we haven't detected the dark matter particles, so probably astrophysical and cosmological observations are the only means to actually infer properties of dark matter. So the Milky Way is the best laboratory, because the precise measurements that we have for the stars in the Milky Way, it's the best compared to we'll ever have for any other galaxies. So then the idea is that we want to probe the nature of dark matter, so know its mass, know its velocity, how it interacts, the fundamental properties that we usually expect to know for any given particle. Also to constrain the gravitational potential of the Milky Way and compare it with the gravitational potential that we get from the galaxies in the simulation based on LambdaCDM model. So trying to constrain the potential of the Milky Way and ultimately compare it what we expect from the theories. Also to constrain the density distribution of dark matter, because even that might, so density distribution of dark matter at Milky Way galaxy scales or even subgalactic scales, because even that might reveal some of the properties of dark matter. So this is the sort of things that we'll talk about now. So we have this, so we want to understand the Milky Way and the dark matter distribution in the Milky Way. So the physical system is Milky Way. The tracer particles, because we cannot see dark matter particle, but the only way to infer its presence or its property is to study objects that we can see, which are stars. So we want to study the dynamics of the stars to understand the property of dark matter. And the idea is pretty simple, because dark matter has mass, so it must interact gravitationally with the stuff that we can see. So by reading off the gravitational imprints of stars, it might encode some information about the distribution of dark matter. So the problem is pretty simple. So what we have is we have 6D information of stars in the galaxy. So we have the X, the position, X, Y, Z. We have V, the position, the velocity of stars, Vx, Vy, and Vz. And the naught here means at the present epoch. So this is something that I'll really appreciate if everyone understands, is that when it comes to galaxies or stars in a galaxy, we only have an observation at the present epoch. So we only have a snapshot of the observation, because the stars are so far off that we cannot really trace their orbits in the time, because as I've already mentioned, that they take million of years, or in some cases billion of years, to really go around the center of the galaxy. So this is not a problem when we do solar system studies, because we can actually see Mars or Mercury really going around the sun. So we know, so their orbits are already constrained. But when it comes to galaxies, we only have a snapshot at a given time, which is an observation taken over the years, but it still will only slightly see stars move. So we really do not constrain the orbit of a star. We have the measurement of their position and velocity at a given epoch. We have other information as well, like the chemical composition of stars, the temperature of stars, but let's leave that aside, because right now we just want to focus on the dynamics. So we have that snapshot distribution, what we physicists like to call the distribution function of the stars, the 6D distribution function of the stars. And then the idea is to understand the 6D distribution of stars, to understand the density the total matter density distribution of the Milky Way, which is a function of the density distribution of stars and gases plus the density distribution of dark matter. So this is something we can know because we can observe. Right? So this is something we can basically calculate just based on observation. So we use this, the 6D distribution function of stars, to calculate the density distribution of dark matter, which ultimately gives us the total density distribution of the Milky Way. But let me try and put this problem in a different perspective that might be familiar for most of us from high school physics. So the idea is that suppose to rephrase that problem in the solar system in the perspective of solar system. So if you only have, so we want to know the gravitational potential of the Milky Way by observing the snapshot of stars. So if you suppose, and just imagine for a while that if you only have the present day positions and velocities of the planets around the sun, do you think we can derive the force law? Or do we think we can derive the mass of the sun, for example? So if you think about it for a while, you'll hopefully realize that it's a hard problem. And it can only be solved under certain assumptions. For example, the system needs to be in equilibrium, so we'll assume if we do not have the full orbits of the planets around the sun, which we do, by the way, because it just takes a couple of years to actually observe planets going around the sun, depending on the distance from the sun. But if we only had a snapshot, then we will have to assume that the solar system is in equilibrium. The solar system is a steady-state system, so the potential is not evolving with time. It's a steady-state system. It's a bound system, so all the planets are bound. There are no flybys some of the planets. It's not that some of the planets are just coming from further out and just passing through the system. We know the 8 planets are really bound to it. The system is long-lived. This is something that, yes, so the system is long-lived. And we will also have to assume the spherical symmetry, just so that problem becomes easy to solve. So in principle, we don't need to assume this for the solar system, because we can basically observe the planets going around the sun. So it's not a problem. We know this is true, more or less. So then it's easy to solve this problem for the solar system. For Milky Way, we have to take certain assumptions, because we don't see stars going around the galaxy. So we don't know what stars are actually part of the Milky Way or are just passing by, or what their orbits are. So we assume that system is in equilibrium. It looks like Milky Way is in equilibrium. It's not just a rush of stars or a gush of stars going around. Seems like it's a steady-state system. We have good reasons to believe that it more or less probably be time independent, the potential of the Milky Way. It looks like a bound system because more or less stars are spherically distributed around the Milky Way. So it looks like it's a bound system. And system is long-lived. This is a constraint that also comes from cosmological simulations. And one thing is that Milky Way is not spherically symmetric, so we incorporate some sort of complexities to account for this problem. And that's when we try to solve the potential of the galaxy using a bunch of stars. But even that turns out as a problem, because stars are not on regular orbits in the Milky Way, right? And we shouldn't expect them to be on regular orbits. So basically, if you have a bunch of stars distributed in the galaxy, they're just moving irregularly. So there's no any uniformity in the distribution of the orbits of these objects. So we want certain probes, so we want certain galactic tool for which we can constrain the orbit, because we know that orbits are very sensitive to the underlying gravitational potential or the underlying matter distribution for a given system. And this is something that comes from, again, high school physics. That if we have different sorts of potential, so here, the red, these are 4 different systems, and the red dot here basically defines the system that we are in. So if there's just a single particle, then we know that the orbit of the tracer particle would be more or less circular. If it's an exponentially decaying disk that can be seen here, if your stars are basically in an exponentially decaying disk form, then the orbits would be a bit more complex. If you have a ring, it will more or less look like a Kepler potential. And if you have a bar, like a chocolate bar placed at the center of the galaxy, then the orbits of the stars would be very chaotic. So we know that the orbits are quite sensitive to the underlying potential of the system. So we need something that looks like orbits so that we can really constrain with impeccable amount the underlying matter distribution of the galaxy, because the ultimate aim is to know the dark matter density distribution in the galaxy. And this brings me back to my very first slide, because this is where the stream, these structures that we are seeing here, these colorful structures that we are seeing, come into the picture, because it doesn't take much and one can easily realize that these string of stars more or less look like orbit already. So basically, these are a bunch of stars that are moving in the same direction, and they can be imagined like orbit segments with stars placed at different time positions along an orbit. So streams, it would be technically wrong thing to say, but streams can serve as a good substitute for orbit that has been cooked by the gravitational potential of the Milky Way. So bingo. So the idea is now to use the position and velocity of these stars to constrain the underlying potential of the galaxy. So I'll come back to that, but let me just first talk a bit about streams, that how do they form in the first place. So I'm showing here again the cosmological simulation, much like I showed before. So you have this main parent galaxy in the middle, and you had the satellite galaxy, the sibling. And as they fall, because of the underlying gravitational potential, the pull of the main galaxy, they basically get stretched by the tidal forces of the parent galaxy, and then they deform. And the star in this falling galaxy begins to distort and escape the potential well of this falling galaxy. And the stars escape. However, they remain on the same orbit of the progenitor, and they end up forming the string of stars that we are seeing here in this simulation. So I know it's a bit messy, but to be quite honest, even the Milky Way is, so we couldn't do any better. This is the end of simulation. So some of the streams, these string of stars that are now formed, can be seen here at the end of the simulation, and these are the remaining progenitors that more or less perhaps didn't disrupt, but these are the tidal debris, the stellar debris that emanated from this falling satellite galaxy. So this is how we understand that these stream structures, these river of stars, form in a given galaxy. So here's one of the example of the stellar streams in the Milky Way in our very own galaxy. So what we are seeing here, it's a density map, and any over density that we are seeing here is basically a star in a given pixel. So this is a star cluster called Palomar 5 cluster. So it was supposed to be a star cluster, but because it came into the influence of the gravitational potential of the Milky Way, the stars began to escape the potential well of this cluster. The cluster stretched, ending up forming the string of stars. And of course, it's more because these arms that are emerging from this cluster, they orient along the same direction as the progenitor system, so the entire structure more or less delineates like an orbit, as can be seen here. And the arrows, of course, mark that the position of the stars align along the velocity vectors of the stars here. So a good substitute for orbits. Milky Way is not the only galaxy that exhibits such streams. So here is Andromeda Galaxy, and one can appreciate a wonderful stream that can be seen here passing around the Andromeda. And these are sort of stream structures, probably not that bright or prominent, but still visible, going around different galaxies in the universe. So the idea is, of course, to extract out these stars and try and constrain the potential of these different galaxies. But again, for most of these external galaxies, we don't have velocities because they're so far off that even if we have a measurement for the velocity, the uncertainty is too high to actually give us any useful results. So that's why we restrain our studies mostly to the Milky Way, to our own backyard, for which we have really good amount of information and deep amount of information. So these are, again, bunch of stream stars that were recently detected with one of the satellites that was sent by European Space Agency. Right. So now, again, going back to the question that we want to probe the nature of dark matter or the gravitational potential of the Milky Way. So different theories of gravity, not just the LambdaCDM model, that's just one theory of gravity. We have different theories of gravity, many of them. We have zoo of them, we have forest of them. And different theories of gravity predict acceleration force field. So what we cannot measure is gravitational potential or the force, but what we can measure is the acceleration along these orbits. So the idea is pretty simple, that these different streams are probing different regions of the sky at different distances, and we can actually measure the acceleration along these orbits, these orbital structures, these string of stars, and then try and compare them against the theories of gravity and see what sort of results we get. So it's really like probing fundamental theories of gravity here. And using these different streams, probing different regions of the sky, we can even imagine constructing a three-dimensional acceleration force field map of the Milky Way. This is a kind of cutting-edge astronomy that people have started talking about only in recent years. The other is, of course, we also want to constrain the gravitational potential of the Milky Way because we want to know the mass of the Milky Way, because that's the only way to actually measure mass. We cannot put a galaxy or any structure on a weighing machine and then weigh it. We need some sort of probes to actually do it. So then we don't know what gravitational potential of the Milky Way is. So we have different forms of gravitational potential. We have different models. And then the idea is to take this model, integrate millions or even billions of orbits if it takes, and try to fit it through the data. So this is the red and blue stars are here data for one of the streams in the Milky Way, in the position space, in distance, in velocity, and also in velocity. And in different potential model, try to fit these integrated orbits through the data and then see which potential model wins. Because the one potential model that is able to best fit through the data sort of suggests that that's the closest that we can get to the actual potential of the galaxy. And ultimately, the idea is, of course, to constrain the shape of the dark matter halo. So the Milky Way galaxy sits in a halo of dark matter. So the sort of constraints that we can talk about is the shape of the halo, that how these dark matter particles are distributed at galactic scales, and also trying to constrain the mass of the Milky Way, because that is also important to put things in cosmological perspective. One of the last things that I would like to talk about is probing the fundamental properties of dark matter. So until now, I've talked about how to use streams to probe galactic scales of matter distribution or dark matter distribution, but really talking about the fundamental properties of dark matter now. So these are 3 different simulations here, produced in a similar way as I've shown before. And here, the only difference between these 3 simulations, the other thing is that all the particles that we are seeing in this simulation is only dark matter. So these are the things we cannot see in real life, but of course we can see it in simulation because that's the game that we are running, so of course we can see it. The only difference between these 3 simulations is that we have changed the mass of the dark matter. That's the only difference. And as one can see that it has repercussions, it has effects on the galactic scales if we change the fundamental property, the mass of the dark matter. So the center here is the center of the galaxy, and all of this is galaxy. And one prominent feature that comes out is that if the mass of the dark matter, if dark matter is really massive, so 10 to the 9 electron volts, for example, then there's too much of substructureness in the galaxy. There are different structures and dark matter subhalos, as we call it over here. And this structureness, this lumpiness, sort of reduces as we go down to the mass of 10 to the 6, of the mass of the order of electrons, so 0.5 mega electron volt. And the structureness sort of reduces. The structureness further reduces, and the dark matter sort of behaves like a gaseous mixture of dark matter particles if we go down to the mass of 10 to the minus 22 electron volts, so almost massless. So basically, by changing the fundamental property, we are changing the dynamics or the structure distribution of dark matter in the galaxies. But then the idea is that can we somehow see this in observation and then try and infer what sort of property dark matter has? So again, streams provide a wonderful avenue to test this. How is that? Remember that stream, the stellar stream, is a continuous string of stars. So one can imagine that as stream evolves or orbits around the galaxy, maybe a given structure, maybe a given non-luminous dark substructure can pass through this stream, continuous string of stars, creating certain perturbation that can eventually evolve in a gap. So the idea is that if you see this continuous string of stars with a gap somewhere in the middle, then that's basically suggesting that at some point in its life, it interacted with, or it collided with a dark matter substructure. So which is kind of nice. And these are the sort of gap features that people are actually seeing now in the observations. So this is one of the very well-famous stream of the Milky Way galaxy, which is called GD1 for some reason. And one can easily notice this gap feature along the stream, which is quite nice. Right, so how to know the nature of dark matter? So you can imagine that if you have different streams probing, again, different region of the sky, different depth of the galaxy, then one can imagine creating this 3-dimensional gap and then trying to see these gaps produced in streams in the Milky Way, and statistically speaking, try to know that what sort of dark matter mass model could have created the number of gaps that we are seeing in different streams. So putting it crudely, if you observe many streams having many gap features, then that would sort of advocate for a dark matter which is very cold and very massive. But if we see streams with more or less no gaps, but sort of fluffiness in the stream with high velocity dispersion, that might advocate for a fuzzy dark matter, meaning very low mass particles. So these are the sort of astrophysical constraints that we are trying to obtain through these studies. So this has brought me to my second last slide. Is I also thought of talking a bit about the Gaia data. So I'm sure everyone is familiar with European Space Agency, which started this very ambitious mission in 2013 of sending a satellite named Gaia in 2013 into the space. And the idea of Gaia is to measure positions and distances and velocities of over billion stars of the Milky Way for the first time with unprecedented accuracy. And of course, the ultimate idea of Gaia mission is to understand the galaxy formation, the galactic structure of the Milky Way, and of course also to nail down the dark matter properties or how it's distributed in the Milky Way. So one thing would probably be nice is to just go on their website, which is very interactive, and try and see what sort of cool science European Space Agency is currently doing. And Gaia is, of course, one of their highlights that might interest you, if none of the previous slides did. Yeah, so coming to the conclusion, LambdaCDM model suggests that 85% of the mass budget of the universe is sourced by the invisible matter, dark matter, and understanding its nature is quite important because it is the main driver of the cosmology of galactic structures at galactic and subgalactic scales. Milky Way is, of course, an amazing laboratory because the amount of information that we'll have for Milky Way at any given era would be much more better than we'll ever have for any other galaxy in the universe. Stellar stream structures offer very exciting avenue to constrain fundamental properties of dark matter, as I've shown, and hopefully you're excited or convinced at some level. And the idea is to understand the morphology or the dynamics of the streams to try and extract out some sort of encoded information in the streams about the dark matter. And yes, the advent of ESA Gaia. So one of the data of ESA, where they gave the position and velocity for many stars in our galaxy last year, has opened an exciting new panoramic window out to our galaxy because they provided velocities for tremendous amount of stars in our galaxy. Thereby, because I'm highlighting because this is something that was done for the first time. Because we deal with velocities every day, but really observing velocities of the stars for galaxies and stars in galaxies is very challenging. So this is something that was done recently. And of course, people are analyzing this data, and they will be analyzing for coming few years, probably decade. So I hope you stay updated with some of the cool science that might lie ahead. Thank you so much for your attention.